Hello friends, welcome to Fluid Mechanics classes. I am Professor Viscous Kumar, Department of Mechanical Engineering, Angadi Institute of Technology and Management, Belagavi. So today's topic is dimensional analysis. In today's class, we are going to discuss about what is the dimension and units and understand the benefits of dimensional analysis and how to use the Buckingham pi theorem and method of repeating variables to get the non-dimensional parameters and understand the dynamic similarity and its applications. These are the reference books I have used to prepare my notes. Fluid Mechanics by Jonas Sanjal and Fluid Mechanics and Hydraulic Machines by R.K. Bansal. So what is a dimension? A dimension is a measure of physical quantity. For example, you take the length. Length is a dimension and the unit, we assign some number to that dimension so that we call it as unit. So what is the unit of length? Unit of length can be centimeters, meters, kilometers. There are 7 primary dimensions. We also call them as fundamental or basic dimensions, namely mass, length, time, temperature, electric current, amount of light, amount of matter. The symbol of mass is written as m, length L, and time t, and temperature as theta. So for any quantity, we have some unit for that. For example, you take the unit of velocity, it's meters per second. So meter. So what is its dimension? Its dimension is length. So I can write meter as, symbolize it as L per second. So what is the dimension of second? It is time t. So I can write the dimension of velocity as L by t. I have listed some of the dimensions of the physical quantities. So it is very important that you have to remember all these dimensions. We are going to use these dimensions in the problems. Sometimes it would be difficult to remember the dimensions, so you better remember the unit. From the unit we can derive the dimensions. In my next slide I have explained with an example how to derive the dimensions from the units. Let's take up an example to understand how to get the dimension for the given quantity. So let's take up angular acceleration. Unit of angular acceleration is radians per second square. So there is no unit for the radian and the dimension of second square is t square. So I can write the dimension of angular acceleration as t raised to minus 2. In a similar way, the unit of discharge is meter cube per second. What is the formula? It is area into of discharge is area into velocity. So what is the unit of area? It is meter square. And what is the unit of velocity? It is meters per second. So when I combine, I get meter cube per second. So what is the dimension of meter? It is length. So meter cube, length cube divided by second, it is divided by t. So I can write this as L cube t to the power minus 1. So the dimension of discharge is L cube t to the power minus 1. Next, let's take up one more quantity, that is kinematic viscosity. So kinematic viscosity is dynamic viscosity divided by density. So dynamic viscosity, it is denoted by symbol nu. So how we got this nu? We got this nu from viscosity expression. Tau is equal to nu dou u by dou y, where this tau is shear stress and dou u by dou y is velocity gradient, where this u represents velocity and this y represents length. Okay, so nu is equal to tau by dou u by dou y. So tau is shear stress and u is velocity and y is length. So I can write this in terms of units as shear stress per velocity per length. Now I need to simplify this till I get one of those 7 primary dimensions. We need to simplify it till we get the primary dimensions. Okay. So shear stress is equal to force by area. So what is force? Force is mass into acceleration by area. Now in the denominator it is velocity per length. What is velocity? Velocity is meters per second divided by length. What is meter? Dimension of meter is length. Okay. Now length get cancels. So what remains in denominator is 1 by second. Okay. So now in the numerator we have mass into acceleration by area. That is, this mass into acceleration is nothing but force. Okay. So now I need to further simplify this acceleration. So what is this acceleration? Acceleration unit is meters per second square. Okay. So mass into meters per second square. Okay, divided by area. So what is the unit of area? Area is meter square. So meter square is written here. Okay, so now we have got all the terms in primary dimension. Okay, let us cancel out the terms and simplify them, and let's write the dimension for the kinematic viscosity. So what is the dimension of mass? It is m. So I have written m here. Okay, so here I have meter and in the denominator meter square. So meter and meter square, one of the meter get cancels, and we get in the denominator meter, and the dimension of meter is length. So when I take it to the numerator, I'll get L to the power minus 1, and again in the denominator I have second square. When I take it to the numerator, it is t to the power minus 2. Okay, now here in the denominator I have 1 by second. So this 1 by second I can write it as t to the power minus 1. So in the numerator here I have t to the power minus 2, t to the power minus 1 in the denominator. So when I take this to the numerator, then this t will be t to the power minus 1. So my expression will be m L to the power minus 1 t to the power minus 1. So now this is the dimension for dynamic viscosity. Okay, this m L to the power minus 1 t to the power minus 1 is the dimension for dynamic viscosity. Now let us find the dimension for density. Density is mass by volume. So mass is, the dimension of mass is m, and unit of volume is meter cube. What is the dimension of meter cube? It is length L cube. So I can write it as m L to the power minus 3. So now kinematic viscosity is equal to dynamic viscosity by density. So expression for dynamic viscosity, that is dimension of dynamic viscosity, is m L to the power minus 1 t to the power minus 1 divided by dimension of density is m L to the power minus 3. So m and m get cancels, and this L to the power minus 3 we take it to the numerator. Okay, so here I have L to the power minus 1 into L cube. I'll get L to the power 2 into t to the power 1. This L square t to the power minus 1, this is the dimension for the kinematic viscosity. So in this fashion we have to find the dimension for any given quantity in the problem. So if they have not given anything, if you can't remember, if you are confused, then the best way is to write the unit, simplify this and get the dimensions. Okay, what is dimensional homogeneity? If you take any equation, okay, the dimensions on the left hand side should be equal to the dimensions on the right hand side. Then we say that the equation is satisfying dimensional homogeneity. Okay, if it is not satisfying, then we are wrong somewhere in the previous steps. Okay, in this regard, I have written a note on dimensional homogeneity. If at some stage of analysis we find ourselves in a position in which two additive terms in an equation have different dimensions, this would be clear indication that we have made an error at some earlier stage in the analysis. So what it means is, somewhere during the solving the problem, if you find that the dimensions of LHS and RHS are not equal, it means that somewhere you have done the mistake. What is non-dimensionalization? It means that removal of units from the physical quantities by a suitable substitution of variables. Non-dimensionalization means making a quantity unitless. Okay. So we'll take up an example so that we understand better. Okay, let's consider equation of motion describing the elevation of an object falling by gravity through a vacuum. The initial location of the object is z0 and its initial velocity is v0 in the z direction. From our high school physics, we have learned the expression for this kind of problem as d square z by dt square minus g. D square z by dt square minus g, and when we put the initial conditions, we get the final expression as z is equal to z0 plus v0 t plus half gt square. So what are those initial conditions? Those initial conditions are z0 and v0. What is that z0? Z0 is the initial location of the object and v0 is initial velocity in the z direction. So here we have 5 parameters, that is z, z0, v0, t and g. Okay, so we have written the dimensions of all the 5 parameters. So z unit is meter and its dimension is L. Z0 is also, its unit is meter and its dimension is L, and time t refers to time and its dimension is t. V0 refers to velocity, initial velocity, unit is meters per second. So meter is length and second is time, so L by t. G is acceleration due to gravity, unit is meter per second square, so meter dimension is length and second square dimension is t square. Okay, so now if you observe here, we have 2 primary dimensions. We do not have mass, we have only length and time, so keep this in mind. Okay, now in the previous equation where we had 5 variables, so out of 5 variables, so there were 2 dimensional variables, means z0 was constant, v0 was constant and g was constant. So only variables were z and t, that is the height and time. Okay, so we need to non-dimensionalize that. We have to use scaling parameters such that the unit of z will get cancels and the unit of time also get cancels. Okay, so we are now going to non-dimensionalize it, means we are going to remove the units of that. Okay, so in this problem our dimensional variables are z and t. Okay, so there are 2 dimensional variables, so we are going to use 2 scaling parameters. Okay, scaling parameters. So what are those scaling parameters we have chosen? We have chosen z0 and v0 as the scaling parameters. Okay, and t are dimensional variables. Okay, dimensional variables means that vary in the problem. Okay, so in that out of 5 parameters, only variables are z and t. So rest 3, that is z0, v0 and g, they are constants. Okay, now we need to non-dimensionalize this z and t. So to non-dimensionalize z and t, I have chosen z0 and v0, that is initial height z0 and initial velocity v0 as scaling parameters. So now we have to divide z by z0. Okay, so whatever non-dimensionalized expression I get, I call it as z star, and similarly I am dividing v0 t by z0. Okay, so here v0 is meters per second into second get cancelled, so units are same in the numerator and denominator. Okay, so when I divide this, whatever expression I get for non-dimensionalized form of t, I get call it t star. Okay, now I have initial equation, that is d square z by dt square is equal to minus g. Wherever z is there, I am going to substitute the expression z is equal to z star into z naught. So here I have substituted for z, replace z by z naught into z star. Okay, so here I have dt square. Wherever t is there, you replace it by t star z naught by v naught. Okay, z naught t star by v naught whole square. Okay, since z naught and v naught, they are constant. Okay, when you take this out, so our expression is v naught square by z naught into d square z by dt square is equal to minus g. Okay, so now when you modify this, when I take this g in the denominator, if you just look at this constants, so I have v naught square by g z naught. Okay, so when I remove this square, okay, then it becomes square root in the denominator. Okay, that is v naught by square root of g z naught. So this v naught by square root of g z naught, okay, so this ratio we call it as Freud number. Okay, so at this point you just follow what I am saying. The whole concept will be understood, okay, when we go for next level. Okay, so as of now you just remember v naught by square root of g z naught, we call it as Freud number. So when I see here I have a Freud number. Okay, when I take this to the RHS, okay, d square z star by dt star square is equal to minus 1 by Freud number square. Okay, so in dimensionless form only one parameter remains, namely Freud number. Above equation can be easily solved by integrating twice and applying the initial conditions. So whatever expression we got in equation number 6, double integrating this and applying the initial conditions, I will get non-dimensionalized results. That is z star is equal to 1 plus t star minus 1 by 2 Freud number square into t square. Okay, so this is the expression, non-dimensionalized expression that I have got. Okay, when I compare the dimensional equation and non-dimensional equation of that problem, so whatever problem we had discussed, okay, so we had derived considering the dimensional equation, and we also got an expression, non-dimensional expression for the same problem. Okay, so the dimensional equation was z is equal to z naught plus v naught t plus half gt square. Okay, wherein we have 5 parameters. It is function of 5 parameters. Okay, but when we non-dimensionalized this equation and we got the expression for the same problem in a non-dimensional form. So look here, we have only 3 parameters. Okay, the number of parameters in a non-dimensionalized equation is less than the number of parameters in original equation. Okay, so now we'll come to know what is the use of studying non-dimensional equation. Okay, in the next slide I will explain you the advantage of this. So in the previous example, we couldn't understand much about the importance of non-dimensionalizing the equation. Okay, you'll understand it in a more better way, more broader way when I take up the same expression but in a different way. Okay, let's take up this example. Your little brother's high school class conducts experiments in a large vertical pipe whose inside is kept under vacuum conditions. The students are able to remotely release a steel ball at initial height of z0 between 0 to 15 meters measured from the bottom of the pipe, and with initial vertical speed v0 between 0 and 10 meters per second. A computer connected to a network of photosensors along the pipe enables students to plot the trajectory of the steel ball for each test. Okay, so when a student drops the ball in a pipe, okay, vacuum pipe, at some height and Z0 and at some velocity V0. Okay, there are computers with photo sensors. Okay, they take the photos of ball at every instant and they plot the graph. Okay, so since the students are unfamiliar with the dimensional analysis or non-dimensionalization technique and therefore conduct several brute force experiments to determine how the trajectory is affected by initial conditions of Z0 and V0. Okay, so students, since they are studying in school, they do not know the dimensional analysis. So to understand the relation between Z0 and V0, they had to conduct so many experiments. Okay, firstly they hold V0 at 4 meters per second and conduct experiments at 5 different values of Z0. So they keep initial velocity a constant 4 meters per second and they conduct the experiment at different heights of 3 meters, 6 meters, 9 meters and 15 meters, and they have, okay, this is the graph. It is fixed. Okay, for different height the graphs are plotted. Okay, and next they fix the Z0 at 10 meters. Okay, and they conduct the experiment at different velocities of 2, 4, 6, 8 and 10 meters per second, and the graphs are plotted. So later in the same evening your brother shows you the data and trajectory plots and tells you that they plan to conduct more experiments at different values of Z0 and V0. You explain him that by first non-dimensionalizing the data, since you know about the non-dimensionalization of the units. Okay, so you explain him the problem can be reduced to just one parameter and no further experiments are required. Okay, so if you non-dimensionalize the data and if you conduct the experiment, he says to his brother that you need to conduct only one experiment. Otherwise, if you go by raw method of conducting the experiment at different heights and at different velocities, you need to conduct large number of experiments to understand the relation between Z0 and V0. Okay, so he uses the same equation that we used in the previous problem. D square Z by dt square is equal to minus G. Okay, the non-dimensionalized equation is that we have here. D square Z star by dt star square is equal to 1 minus 1 by Reynolds number square. This problem combines three of the original dimensional parameters, that is G, Z0 and V0, in one dimensional parameter Reynolds number. Means, so whatever three parameters we had in the dimensional equation, so all the three parameters are combined and it is written in only one form, one non-dimensional form. So that is nothing but the Reynolds number. After converting into dimensionless variables, that is Z star is equal to Z by Z0 and T star is equal to V0 T by Z0, the 10 trajectories are plotted in dimensionless format. So after converting into non-dimensional form, okay, they have plotted the graph. It is clear that all the trajectories are of the same family with Reynolds number as the only remaining parameter. If you look at the graph, so all the graphs are of the same family. Okay, there is no variation. Reynolds number square varies from 0.41 to about 1 in these experiments. If any more experiments are to be conducted, they should include combination of Z0 and V0 that produce Reynolds numbers outside of this range. A large number of additional experiments would be unnecessary since all the trajectories would be of the same family as those plotted. So what we can understand from this example is that instead of conducting the experiments for so many numbers, okay, we can non-dimensionalize the terms and we can conduct very few experiments and we can get the same results by conducting few number of experiments. So that is one of the advantage of non-dimensionalizing the terms. By conducting the experiment using the Froude number, what we can conclude is that at low Froude numbers, gravitational force are much larger than inertial forces and ball falls to the ground in relatively short time. And at large Froude numbers, inertial forces dominate and ball rises significant distance before falling. It takes much longer for the ball to hit the ground. Okay, with whatever information we have got, whatever we have studied till now, so all this information will help us in understanding the dimensional analysis in a better way. Okay, so the first question is why we need to study dimensional analysis. So in real life engineering, the equations are either not known or too difficult to solve. Often experiment is the only method of obtaining the reliable information. In most experiments, to save time and money, tests are performed on geometrically scaled model, okay, rather than on a prototype. Okay, we'll see what is model and what is prototype. So powerful technique called as dimensional analysis will help us in this regard. It is useful in all disciplines, especially when it is necessary to design and conduct experiments. So what is model? So model is a small scale replica of actual structure or machine. So you want to construct a shape, okay, so before constructing a shape we are going to construct a small model of that, okay, small structure of that. So that small structure we call it as model. So prototype is the actual structure or machine is called a prototype. Okay, if you are going to make a ship of its original dimensions, okay, then we call it as prototype. Okay, so there are three necessary conditions, okay, to compare, to relate model and prototype. First one is geometric similarity. So what is geometric similarity? The model must be the same shape as the prototype. So if you look at so this is a prototype car, okay, that we want to run, which runs on the road, okay, but before constructing this prototype car we are going to construct the small model, the scaled down, okay, structure of that car. That scaled down structure of that car we call it as model, okay, and we are going to study all the effects on this, and next we design it. So this we call it as geometric similarity. Next one is the kinematic similarity, which means that the velocity at any point in the model flow must be proportional to the velocity at the corresponding point in the prototype flow. Okay. For kinematic similarity, the velocity as corresponding point must scale in magnitude and must point in the same relative direction. Okay, so if a kinematic similarity means the direction of velocity components, in which direction they are showing. Okay, velocity is a vector quantity. It has both magnitude as well as direction. Okay, the velocity on the model should be in the same direction. Its magnitude can vary, okay, depending on the multiplication, okay, but the direction should not change. And the last similarity is dynamic similarity. All the forces in the model flow must scale by a constant factor to the corresponding forces in the prototype flow. In other words, the relative importance of different types of forces, example viscous and inertial forces, must be the same for model and the prototype. This requires that model and prototype have the same dimensionless parameters like Reynolds number, okay, although they may have different dimensional variables. So I have written a note. In a general flow field, a complete similarity between a model and prototype is achieved only when there is a geometric, a kinematic and dynamic similarity. Okay, so as of now you just understand what is geometric, kinematic and dynamic similarity. So again we are going to study all the three separately in detail. Okay, once we finish this dimensional analysis. So we are into important concept, that is Buckingham pi theorem. So what is Buckingham pi theorem? So basically Buckingham pi theorem will help us in identifying the non-dimensional parameters. Okay, so it gives us the procedures as to how to get the non-dimensional parameters. Okay, if there are n variables, suppose there are n variables, both dependent and independent. Okay, so in a physical phenomena, and if these variables contain m fundamental dimensions. Okay, so in almost we have three fundamental dimensions come across in mechanical problems, that is mass, length and time, and sometimes two fundamental dimensions like the last problem. Okay, then the variables are arranged into n minus m dimensionless terms. Okay, suppose there are n variables, n is equal to 10 and fundamental dimensions m is equal to 3, then total number of pi terms, we call it as pi terms, is equal to n minus m. 10 minus 3 is equal to 7, so total pi terms are 7. Okay, so we'll see all this. Okay, what is this pi term and how the procedure, how to get all this. So let us assume that x1, x2, x3, in this fashion xn are the variables involved in a physical problem. Okay, and x1 is a dependent variable. Okay, and x2 up to xn are independent variable. So x1 depends on x2, x3 up to xn. So x1, it is function of x2, x3, xn. So total number of variables, that is n equal to, okay, it is sum of independent and dependent variables. Okay, so I can also write this equation as function of x1, x2, x3 up to xn is equal to 0. Okay, so above equation is a dimensionally homogeneous equation. It contains n variables. So total number of variables are sum of dependent variables as well as independent variables. So the total number of variables in that problem, we call it as n. Okay, if there are m fundamental dimensions, then according to Buckingham's pi theorem, above equation can be written in terms of number of dimensionless groups or pi terms. Okay, so these are number of terms, okay, minus dimensionless minus fundamental dimensions. Okay, suppose say in our problem fundamental dimensions are 3, then n minus m, okay, are our pi terms. Okay, we are converting those dimensionless terms into dimensional terms into dimensionless terms. Okay, so here I am just explaining you theoretically. Okay, so once we go to the example, you will understand this in a better way, and it is most easiest step. Okay, you can easily do it provided if you remember the dimensions for all the physical quantities. Okay, so our pi terms will be pi 1, pi 2, pi 3 up to pi n minus m. So each of pi term is dimensionless and is independent of the system. Okay, so pi 1 is equal to x2 to the power a1. Okay, you can just go through this. Okay, so basically here he has explained the procedure. Okay, how to get the non-dimensional parameters, steps. Okay, Buckingham pi theorem, these are the steps. Okay, so we'll understand this in a better way when we go to the examples. So what is the method of repeating variables? We can think of this method as step-by-step procedure or recipe for obtaining non-dimensional parameters. There are 6 steps listed concisely. These steps are explained in further details as we work through the number of examples. Okay, so whatever we discussed just previously under the Buckingham pi theorem heading. Okay, so all those is written just in steps. Okay, so we'll just quickly read this. Step 1, list the parameters, dimensional variables, non-dimensional variables and dimensional constants and count them. Let n be the number of parameters in the problem including the dependent variable. Okay, make sure that any listed independent parameter is indeed independent of others, that is it cannot be expressed in terms of them. Example, don't include radius r and area A is equal to pi r square since r and A are not independent. Okay, that is step 1. Step 2 is list the primary dimensions for each of the n parameters. Okay, so in the problem they'll give you some parameters, okay, like density, viscosity, speed, acceleration. Okay, so these are the parameters. For each parameters we have to write the dimensions. So that's what I told you, it's very important, you need to practice. Okay, you need to remember the dimensions of all the physical quantities. So step 2 is list the parameters of each of n parameters. Okay, so next step 3 is guess the reduction m. Okay, means as the first guess, set m equal to number of primary dimensions represented in the problem. Okay, suppose once you write the dimensionless parameters, you just observe dimensionless parameters. Okay, so number of primary dimensions involved in that. If there are 3 primary dimensions, then you set your m value equal to 3. If you find the primary dimensions equal to 2, like the problems that we solved in the beginning. Okay, so there we did not had mass, we had only length and time. So in those cases set m is equal to 2. Okay, then the expected number of pi terms will be equal to number of variables minus m. Okay, so next one is step 4, choose m repeating parameters that will be used to construct each pi term. Since the repeating parameters have the potential to appear in each pi, be sure to choose them wisely. Okay, so how next step 5 is generate the pi's, okay, one at a time by grouping the m repeating variables parameters with one of the remaining parameter, forcing the product to be dimensionless. In this way construct all k pi's. By convention, the first pi designated as pi 1 is the dependent pi. Manipulate the pi's as necessary to achieve established dimensionless groups. Step 6 is check that all pi's are indeed dimensionless. Write the final functional relationship. Okay, so basically here they have explained us the procedure as to how to get the pi terms and how to get the dimensionless terms. Okay. Here are the guidelines to choose number of repeating variables m. So in the previous slide you had seen m. So total number of pi terms is equal to total number of variables n minus number of repeating variables m. Okay, now how to choose that? So there are you cannot just choose those variables just like that. Okay, we need to follow some rules to choose the repeating variables. Okay, what is that? The first rule is never pick the dependent variable. Okay, so never pick the dependent variable. If x1 is function of f of x2, x3, x4, then never pick x1 because x1 is a dependent variable. Okay, second one is the repeating variables selected should not form a dimensionless group. Okay, so you should not choose those variables as repeating variables which themselves form as a dimensionless group. Okay, and third step is the chosen repeating parameters must represent all the primary dimensions in the problem. So whatever the repeating parameters you are choosing, out of the given parameters in the problem. Okay, so all the repeating parameters should contain the primary dimensions. Okay, never pick the parameters that are already dimensionless. That's what you should not choose a parameter which is dimensionless. Okay, next fifth one is never pick two parameters with the same dimensions or with the dimensions that differ by only an exponent. Okay, we have to choose a repeating variable which contains different dimensions, not the same dimensions. Okay, and the sixth rule is whenever possible choose dimensional constants over the dimensional variables so that only one pi contains the dimensional variable. Okay, so wherever possible in the problem try to choose dimensional constants. Okay, dimensional constants, not the dimensional variables. One which varies, don't prefer that. Okay, one which is constant, you prefer that. Okay, like in our first problem, dimensional variables were z and t, whereas dimensional constants were z0 and v0. Okay, prefer z0 and v0 as repeating variables over the z and t. Okay, next pick common parameters since they may appear in each of the pi terms. Okay, so pick simple parameters over complex parameters, means 7 and 8 are almost same. Okay, we need to choose such parameters which are easy to remember for us. Okay, which are easy to remember and which are easy to reproduce dimensions. Okay, next one, the repeating variables should be chosen in such a way that one variable contains geometric property and other variables contains flow property, and the third variable contains fluid property. We have to choose the repeating variables in such a way that okay, geometric property, flow property, and one more is flow property, and all the three should contain geometric property, flow property, and fluid property. Okay, so we have to choose the parameters such that it should be part of all the three. We have to choose each parameter from each one: geometric, flow, and fluid property. Okay, I have just written few examples for understanding purpose. Geometric properties is like length, diameter, height. Flow properties are like velocity and acceleration, and fluid properties are like viscosity, density. Buckingham pi theorem, and we have seen the rules. Okay, so now let us understand the Buckingham pi theorem by considering the example. So here I have chosen the same example that we discussed in the beginning in the non-dimensional concept. Okay, so there we knew the parameters. Okay, so here let us assume that we don't know anything in this problem. We'll consider the same problem. Okay, so we don't know anything. Okay, we just know that the ball that falls from a height, it depends on height z and time t. So it is just function of z and t. We do not know anything. Okay, let us consider a ball falling in a vacuum. I discussed before. Let us pretend that we do not know that equation d square z by dt square is equal to d is appropriate for this problem. Means we do not know, even we don't know that formula also. Okay, nor do we know much physics concerning falling objects. Okay, in fact, suppose that all we know is that the instantaneous elevation z of the ball must be a function of time t. Initial vertical speed v0, initial elevation z0, and gravitational constant g. Okay, so we just know that when a ball falls, elevation of ball, so z is function of time and initial velocity and initial elevation z0 and gravitational constant g. The beauty of dimension analysis is that the only other thing we need to know is the primary dimensions of each of these quantities. Okay, so we have considered the same example here. Okay, wherein the elevation of the ball, it is function of time, velocity, elevation, and g. Only this much we know. We do not know anything. Okay, now using the Buckingham pi theorem, non-dimensionalization concept, okay, we are going to obtain the expression, okay, for non-dimensional parameters. Solve this problem step by step. Okay, step 1, there are 5 parameters: dimensional variables, non-dimensional variables, and dimensional constants in this problem. N is equal to 5. Okay, so z, it depends on time, initial velocity, initial height, and g. Okay, so total number of parameters are 1 2 3 4 5. So n is equal to 5. Here z is dependent variable and all these 4 are independent variable. Okay, so the next step is we need to write the dimension for all this. Okay, so what is the unit of z? It is meter. Okay, so I have written here m to the power 0. So you know that anything to the power 0 is 1. Okay, so here d naught is also 1. So what remains is L1. Okay, so for understanding purpose, we have to make this as a practice. Okay, if nothing is there, you just write in it that to the power 0. It is nothing but 1. Okay, and here time. Okay, t1, whereas m naught and L naught. Okay, and velocity meters per second. Meter is length per second. T to the power 1. So m naught is nothing but 1. Okay, L1 t to the power minus 1. Okay, in a similar fashion we have written the dimension for z naught and the dimension for g. Okay, so next, third step is when we observe the dimensions of all the 5 variables, we see that there are only 2 primary dimensions involved. Hence we can consider m is equal to 2. If you look at the dimensions of all this, okay, so there is no mass involved here. Okay, here also m is to the power 0, m to the power 0, m to the power 0, m to the power 0, and m to the power 0. So mass is not there. Okay, so we can choose m is equal to 2. Okay, then our total number of pi terms is equal to n minus m, that is 5 minus 2. So 5 is total number of variables and 2 is m. Okay, so the number of pi terms are 3. Okay, so I can call them as pi 1, pi 2, pi 3. Okay, now m is equal to 2. Then we need to choose 2 repeating variables. Okay, total number of variables are 5. Out of 5 we need to choose 2 repeating variables. Okay, and first condition is what? We cannot select dependent variable. So choosing this z is ruled out. Z is a dependent variable and should not be selected. Okay, now total number of variables remaining are 4. Now out of these 4 we need to choose 2 repeating variables. Okay, so out of the 4 variables, one variable should have geometric property, the second variable should have flow property. Okay, so these requirements are fulfilled by selecting z naught. So z naught, it is which property? It comes under geometric property. And velocity, okay, it comes under flow property. Okay, so the repeating variables themselves should not form a dimensionless term and should have themselves primary dimensions. So this contains primary dimensions and they themselves do not form a dimensional terms. Okay, so the dimensions of z naught and v naught are L to the power 1 and v naught is L1 t to the power minus 1, and hence 2 primary dimensions. If you just observe the dimensions here, we have 2 dimensions. Okay, exist. Okay, now we combine these repeating parameters into products with each of the remaining parameters one at a time to create pi terms. The first pi is always a dependent pi and is formed with dependent variable z. Okay, now look here carefully. So pi 1 is, I have chosen z naught and v naught as repeating variables. So I write this as z naught a to the power 1 and v naught a to the power b1. Okay, so now when I choose z naught and v naught as repeating variables, okay, there are 3 variables which are left. Okay, so there were totally 5 variables. Now out of 5 variables I have chosen 2 as repeating variables, means all these repeats in each and every equation. So when I choose these 2, so total number of variables remaining are 3. Okay, so pi 1 is equal to z naught v naught a1 to the power a1 b1, and out of remaining 3 I am writing one term here, z. Okay, so this is my pi 1, one dimensionless term. Okay, now pi 2 is z naught a2 v naught b2, and out of that 2, okay, z was already written and remaining was t and g. I am writing t here. Okay, next, this is one dimensionless term. Now pi 3 is equal to z naught a3 v naught b3, remaining is g. Okay, so now total number of pi terms, how much we get? N minus m, that is 5 minus 2 is equal to 3. So these three, pi 1, pi 2, pi 3 are our dimensionless terms. Understood? Okay. So now we need to consider each pi term, okay, and write the dimension for Z0, V0 and Z, okay, and equate LHS and RHS, the powers of the dimensions in left hand side and right hand side, and get the expression for A1 and B1. Okay, so let us consider the first pi term. Okay, so pi 1, it is dimensionless, so I have written M0, L0, T0 because it is dimensionless, equal to, what is Z0? You have already written the dimensions of Z0, it is M0, L1, T0 to the power A1, and already you know the dimensions of V0, that is L1 T to the power minus 1 V1, and Z, its dimension is L1. Okay, so just for practice purpose I have written M to the power 0. Anything to the power 0 is 1. You can either write it or you can leave it. Okay, just for practice purpose I have written 1. Now what we are going to do is we are going to compare the powers of the dimensions on LHS and RHS. Suppose if I take mass, the LHS, the power is 0. I have written 0, and in the RHS the power of M is 0 everywhere, so I have written 0. Okay, now let us consider the power of length. On the left hand side it is 0, I have written 0 here. Okay, now let us look at the right hand side. Here I have L to the power 1, okay, and whole to the power A1. So what is this? A1. Okay, I have written A1 here, power of L. Okay, plus here I have L1 and whole power B1, so I can write plus B1, and here it is L1, so the power of L is 1, so I have written 1, so power of L is 0 is equal to A1 plus B1 plus 1. Okay, now let us compare the power of T, time. On the left hand side it is 0, and here also it is 0, T to the power 0 and T1, it is nothing but T to the power 0, the power is 0, and here I have minus 1 to the power B1, so it is minus B1, so minus B1 plus here it is T to the 0, T to 0. Okay, so now from this equation what we get? B1 is equal to 0. So if I substitute B1 equal to 0 in the above equation, A1 is equal to minus 1. So now we know the value of A1 and value of B1. Okay, we will substitute A1 and B1 in this equation. Pi 1 is equal to Z0 A1. Z0 A1 is minus 1, so Z0 minus 1. Okay, and V0 B1, V0 B1 is B1 is 0. Okay, so what I get? Pi 1 is equal to Z by Z0 minus 1. I can write this in denominator. So pi 1 term we got Z by Z0. Okay. So in a similar fashion we will find pi 2 and pi 3. So we will take the equation of pi 2. Pi 2 is dimensionless, so M0, L0, T0 I have written. On the right hand side I have written dimensions of Z0 with A2 as the whole power, and V0 with B2 as whole power, and time. Okay, T1. Okay, let us compare the powers of M and powers of L and powers of T. Okay, so power of M is 0, 0, power of L on the left hand side it is 0, and on the right hand side it is L to the power 1 into A2, so A2, and here also I have L1, so it is plus B2, and here it is 0, so A2 plus B2 is equal to 0, so A2 is equal to minus B2. Now let us compare the power of T, that is on the left hand side T to the power 0, so the power is 0 here, and T to the power 0 into A2 is nothing but 0, so 0, here T to the power minus 1 into B2 I have, so it is minus B2, and here T to the power 1 I have plus 1, so B2 is equal to 1. Okay, now I got what is the value of B2. When I substitute here I'll get the value of A2, so A2 is minus 1, B2 is plus 1. Okay, I'll substitute the value of A2 and B2 in pi 2 equation. Okay, when I substitute it is Z0 minus 1, V0 1 T. Okay, so Z0 minus 1 I can take it in denominator, so V0 T by Z0. So I got pi 2 term. Pi 2 term is equal to V0 T by Z0. You just go back and you check your dimensionless terms that we got, z star is equal to z by z naught. Okay, so that we got as pi 1 term, and one more term we had got as t star is equal to v naught t by z naught. So here look here, pi 2 is equal to v naught t by z naught. So that is the beauty of dimensional analysis. Okay, so similarly it is pi 3, it is not pi 2. Okay, similarly we get the pi 3 term as gz naught by v naught in a similar fashion. Okay, to compare the powers of LHS and RHS, okay, dimensions, and find the unknowns a3 and b3, okay, and substitute in pi 3 equation, you will get the expression for pi 3 as gz naught by v naught. So now all the pi terms have been found, pi 1, pi 2, pi 3. Okay, we see that pi 1 and pi 2 are the same as non-dimensionalized variables z star and t star. Okay, so no manipulation is necessary for this. However, we recognize that the pi 3 term, okay, must be raised to power minus half to be of the same form as an established dimensionless parameter, namely the Froude number. If you look at the Froude number, so what the Froude number expression? So v naught by z square root of gz naught. Okay, so whereas our dimensionless pi 3 term is gz naught by v naught square. Okay, so to get this in this form, we need to multiply minus half, we need to power, okay, minus half, then we get the Froude number. Okay, so there are rules for this that we will take up in the next coming slides. Okay, so how to manipulate the pi terms. Okay, such manipulation is often necessary to put the pi's into proper established form. Pi 3 equation that we got is not wrong. Okay, so whatever pi 3 we had found out, that is not wrong. Okay, and there is certainly no mathematical advantage of pi 3 modified. Okay, whatever pi 3 modified we have got. Okay, we have got pi 3 term 1 and we have modified that pi 3 by putting the power minus half so that we get Froude number. Okay, instead we like to say that pi 3 modified is more socially accepted. Okay, more socially accepted means most of the people are familiar with this kind of expression, so we need to modify this. Otherwise pi 3 is also correct. Okay, since it is named established non-dimensional parameter that is commonly used in the literature. So we are finally into the last step wherein we are going to combine all these pi terms. Okay, so we are finally ready to write the functional relationship between the non-dimensional parameters combining all three pi terms. Okay, relationship between the pi terms. So pi 1 was dependent pi term because we had multiplied z there, and pi 2, pi 3 were independent. So pi 1 expression we got it as z by z naught. Okay, equal to function of pi 2 term we got v naught t by z naught, and pi 3 as we modified this. Okay, so in terms of non-dimensional variables z star and t star defined previously, and the definition of Froude number. So final result of non-dimensional analysis is, okay, so we had written this as z star. Okay, z star is function of t star and Froude number. Okay, so we have non-dimensionalized expression, we got the non-dimensionalized expression. Okay, so this is how we have to solve the problems. Limitation for using the dimensional analysis: the method of repeating variables cannot predict the exact mathematical form of the equation. Okay, so if you are going for dimensional analysis, you cannot get the equation. Okay, but we get the dimensionless terms. Okay, so the major disadvantage is we cannot obtain the equations, relations between these terms, but we get the dimensionless groups. Here are the guidelines how to manipulate the pi terms. Okay, the first one is we may impose a constant exponent on pi term or perform functional operation on a pi term. We may raise pi to any exponent n without changing the dimensionless structure of pi. For example, in the present problem we imposed an exponent of minus half, so we converted that pi 3 by putting minus half exponent and pi 3 modified. Okay, so we can do that unless and it should not affect the dimensionless structure of that parameter. Okay, similarly we can perform the functional operations, we can sign, we can use exponents. Okay, so second manipulation we can use, we may multiply pi by a pure constant. Okay, like you can multiply the pi term by half, 2, 4. Okay, we can do that. Okay, and next one, we may form a product of pi terms, like we can replace pi 3 by pi 3 into pi 1 or pi 3 by pi 2. Okay, so all this we can do. These are nothing but manipulation of pi terms. Okay, so in order to get more socially accepted pi terms. Okay, next one, we may use any of the guidelines 1 2 3 combination. We can use combination of all three. Okay, and next last one is we may substitute a dimensional parameter in pi with other parameters of the same dimension. Okay, if there is any parameter of the same dimension, you can substitute that even the pi term also. Okay, so this is the theory part. Okay, so next we'll see few examples wherein you will understand, okay, in a better way. Thank you for watching the video.